Number theory or arithmetic is a branch of pure mathematics devoted primarily to the study of the natural numbers and the integers. It is sometimes called the Queen of Mathematics because of its foundational place in the discipline. Number theorists study prime numbers as well as the properties of objects made out of integers or defined as generalizations of the integers. Integers can be considered either in themselves or as solutions to equations. Questions in number theory are often best understood through the study of analytical objects that encode properties of the integers, primes or other number-theoretic objects in some fashion. One may also study real numbers in relation to rational numbers, e.g., as approximated by the latter. The older term for number theory is arithmetic. By the early 20th century, it had been superseded by number theory. The use of the term arithmetic for number theory regained some ground in the second half of the 20th century, arguably in part due to French influence. In particular, arithmetical is preferred as an adjective to number theoretic. History. Origins. Dawn of arithmetic. The first historical find of an arithmetical nature is a fragment of a table. The broken clay tablet Plimt in 322 contains a list of Pythagorean triples, i.e., integers such that the triples are too many and too large to have been obtained by brute force. The heading over the first column reads, "The tacletum of the diagonal which has been subtracted such that the width." The table's layout suggests that it was constructed by means of what amounts, in modern language, to the identity, which is implicit in routine Old Babylonian exercises. If some other method was used, the triples were first constructed and then reordered by presumably for actual use as a table, i.e., with a view to applications. It is not known what these applications may have been, or whether there could have been any. Babylonian astronomy, for example, truly flowered only later. It has been suggested instead that the table was a source of numerical examples for school problems, while Babylonian number theory, or what survives of Babylonian mathematics that can be called thus, consists of this single, striking fragment. Babylonian algebra was exceptionally well developed. Late Neoplatonic sources state that Pythagoras learned mathematics from the Babylonians. Much earlier sources state that Thales and Pythagoras traveled and studied in Egypt. Euclid IX 21-34 is very probably Pythagorean. It is very simple material, but it is all that is needed to prove that is irrational. Pythagorean mystics gave great importance to the odd and the even. The discovery that is irrational is credited to the early Pythagoreans, by revealing that numbers could be irrational. This discovery seems to have provoked the first foundational crisis in mathematical history. Its proof or its divulgation is sometimes credited to Hippasus, who was expelled or split from the Pythagorean sect. This forced a distinction between numbers, on the one hand, and lengths and proportions, on the other hand. The Pythagorean tradition spoke also of so-called polygonal or figure-eight numbers, while square numbers, cubic numbers, etc., are seen now as more natural than triangular numbers, pentagonal numbers, etc. The study of the sums of triangular and pentagonal numbers would prove fruitful in the early modern period. We know of no clearly arithmetical material in ancient Egyptian or Vedic sources, though there is some algebra in both. The Chinese remainder theorem appears as an exercise in Sun Zi's Suanqing, also known as the mathematical classic of Sun Zi. There is also some numerical mysticism in Chinese mathematics, but, unlike that of the Pythagoreans, it seems to have led nowhere. Like the Pythagoreans' perfect numbers, magic squares have passed from superstition into recreation. Classical Greece and the early Hellenistic period. Aside from a few fragments, the mathematics of classical Greece is known to us either through the reports of contemporary non-mathematicians or through mathematical works from the early Hellenistic period. In the case of number theory, this means, by and large, Plato and Euclid, respectively. Plato had a keen interest in mathematics, and distinguished clearly between arithmetic and calculation. It is through one of Plato's dialogues, namely, Theaetetus, that we know that Theodorus had proven that are irrational. Theaetetus was, like Plato, a disciple of Theodorus's. He worked on distinguishing different kinds of incommensurables, and was thus arguably a pioneer in the study of number systems. Euclid devoted part of his Elements to prime numbers and divisibility, topics that belong unambiguously to number theory and are basic to it. In 1773, Lessing published an epigram he had found in a manuscript during his work as a librarian. It claimed to be a letter sent by Archimedes to Eratosthenes. The epigram proposed what has become known as Archimedes' cattle problem. Its solution requires solving an indeterminate quadratic equation. As far as we know, such equations were first successfully treated by the Indian school. It is not known whether Archimedes himself had a method of solution. Diophantus. Very little is known about Diophantus of Alexandria. He probably lived in the 3rd century CE, that is, about 500 years after Euclid. 6 out of the 13 books of Diophantus's Arithmetic survive in the original Greek. 4 more books survive in an Arabic translation. The Arithmetic is a collection of worked-out problems where the task is invariably to find rational solutions to a system of polynomial equations, usually of the form or. Thus, nowadays, we speak of Diophantine equations when we speak of polynomial equations to which rational or integer solutions must be found. One may say that Diophantus was studying rational points, i.e., points whose coordinates are rational, on curves in algebraic varieties. However, unlike the Greeks of the classical period, who did what we would now call basic algebra in geometrical terms, Diophantus did what we would now call basic algebraic geometry in purely algebraic terms. In modern language, what Diophantus did was to find rational parametrizations of varieties, that is, given an equation of the form. His aim was to find 3 rational functions such that, for all values of n, setting for gives a solution to. Diophantus also studied the equations of some non-rational curves, for which no rational parametrization is possible. He managed to find some rational points on these curves by means of what amounts to a tangent construction. Translated into coordinate geometry, his method would be visualized as drawing a tangent to a curve at a known rational point, and then finding the other point of intersection of the tangent with the curve. That other point is a new rational point. While Diophantus was concerned largely with rational solutions, he assumed some results on integer numbers. In particular that every integer is the sum of 4 squares. Aryabhata, Brahmagupta, Bhaskara. While Greek astronomy probably influenced Indian learning, to the point of introducing trigonometry, it seems to be the case that Indian mathematics is otherwise an indigenous tradition. In particular, there is no evidence that Euclid's Elements reached India before the 18th century. Aryabhata showed that pairs of simultaneous congruences could be solved by a method he called Kutika, or pulverizer. This is a procedure close to the Euclidean algorithm, which was probably discovered independently in India. Aryabhata seems to have had in mind applications to astronomical calculations. Brahmagupta started the systematic study of indefinite quadratic equations, in particular, the misnamed Pell equation, in which Archimedes may have first been interested, and which did not start to be solved in the West until the time of Fermat and Euler. Later Sanskrit authors would follow, using Brahmagupta's technical terminology. A general procedure for solving Pell's equation was finally found by Jayadeva. The earliest surviving exposition appears in Bhaskara-I's Bija-Ganita. Indian mathematics remained largely unknown in Europe until the late 18th century. Brahmagupta and Bhaskara's work was translated into English in 1817 by Henry Colebrook. Arithmetic in the Islamic Golden Age. In the early 9th century, The Caliph al-Ma'mun ordered translations of many Greek mathematical works and at least one Sanskrit work. Diophantus's main work, the Arithmetica, was translated into Arabic by Custer ibn Luca. Part of the treatise al-Faqra builds on it to some extent. According to Rashed Roshdi, al-Karaji's contemporary Ibn el-Haytham knew what would later be called Wilson's theorem. Western Europe in the Middle Ages, other than a treatise on squares in arithmetic progression by Fibonacci, who lived and studied in North Africa and Constantinople during his formative years. California, 1175 to 1200. No number theory to speak of was done in Western Europe during the Middle Ages. Matters started to change in Europe in the late Renaissance, thanks to a renewed study of the works of Greek antiquity. A catalyst was the textual emendation and translation into Latin of Diophantus's Arithmetica. Early modern number theory Fermat Pierre de Fermat never published his writings. In particular, his work on number theory is contained almost entirely in letters to mathematicians and in private marginal notes. He wrote down nearly no proofs in number theory. He had no models in the area. He did make repeated use of mathematical induction, introducing the method of infinite descent. One of Fermat's first interests was perfect numbers and amicable numbers. This led him to work on integer divisors, which were, from the beginning, among the subjects of the correspondence that put him in touch with the mathematical community of the day. He had already studied Bachet's edition of Diophantos carefully. By 1643, his interests had shifted largely to Diophantine problems and sums of squares. Fermat's achievements in arithmetic include Fermat's little theorem, stating that, if A is not divisible by a prime p, then, if A and B are coprime, then is not divisible by any prime congruent to -1 modulo 4, and every prime congruent to 1 modulo 4 can be written in the form. These two statements also date from 1640. In 1659, Fermat stated to Huygens that he had proven the latter statement by the method of infinite descent. Fermat and Frenicle also did some work on other quadratic forms. Fermat posed the problem of solving as a challenge to English mathematicians. The problem was solved in a few months by Wallis and Brunker. Fermat considered their solution valid, but pointed out they had provided an algorithm without a proof. He states that a proof can be found by descent. Fermat developed methods for finding points on curves of genus 0 and 1. As in Diophantus, there are many special procedures and what amounts to a tangent construction, but no use of a secant construction. Fermat states and proves in the appendix to Observations on Diophantos that has no non-trivial solutions in the integers. Fermat also mentioned to his correspondence that has no non-trivial solutions, and that this could be proven by descent. The first known proof is due to Euler. Fermat's claim to have shown there are no solutions to for all appears only in his annotations on the margin of his copy of Diophantus. He never claimed this to others and thus would have had no need to retract it if he found any mistake in his supposed proof. Euler. The interest of Leonhard Euler in number theory was first spurred in 1729, when a friend of his, the amateur Goldbach, pointed him towards some of Fermat's work on the subject. This has been called the rebirth of modern number theory. After Fermat's relative lack of success in getting his contemporaries' attention for the subject, Euler's work on number theory includes the following proofs for Fermat's statements. This includes Fermat's little theorem, the fact that if and only if initial work towards a proof that every integer is the sum of 4 squares, soon improved by Euler himself, the lack of non-zero integer solutions to Pell's equation, first misnamed by Euler. He wrote on the link between continued fractions and Paul's equation, first steps towards analytic number theory. In his work of sums of 4 squares, partitions, pentagonal numbers, and the distribution of prime numbers, Euler pioneered the use of what can be seen as analysis in number theory. Since he lived before the development of complex analysis, most of his work is restricted to the formal manipulation of power series. He did, however, do some very notable early work on what would later be called the Riemann's eta function, quadratic forms. Following Fermat's lead, Euler did further research on the question of which primes can be expressed in the form, some of it prefiguring quadratic reciprocity. Diophantine equations. Euler worked on some Diophantine equations of genus 0 and 1. In particular, he studied Diophantus's work. He tried to systematize it, but the time was not yet ripe for such an endeavor. Algebraic geometry was still in its infancy. He did notice there was a connection between Diophantine problems and elliptic integrals, whose study he had himself initiated. Lagrange, Legendre and Gauss. Joseph Louis Lagrange was the first to give full proofs of some of Fermat's and Euler's work in observations, for instance, the four-square theorem and the basic theory of the misnamed Pell's equation. He also studied quadratic forms in full generality, defining their equivalence relation, showing how to put them in reduced form, etc. Adrien Marie Legendre was the first to state the law of quadratic reciprocity. He also conjectured what amounts to the prime number theorem and Dirichlet's theorem on arithmetic progressions. He gave a full treatment of the equation and worked on quadratic forms along the lines later developed fully by Gauss. In his old age, he was the first to prove Fermat's last theorem. 4. In his Disquisitiones Arithmetici, Carl Friedrich Gauss proved the law of quadratic reciprocity and developed the theory of quadratic forms. He also introduced some basic notation and devoted a section to computational matters, including primality tests. The last section of the Disquisitiones established a link between roots of unity and number theory. The theory of the division of the circle, which is treated in Sec. 7, does not belong by itself to arithmetic, but its principles can only be drawn from higher arithmetic. In this way, Gauss arguably made a first foray towards both Évariste Galileois's work in algebraic number theory, maturity and division into subfields starting early in the 19th century. The following developments gradually took place. The rise to self-consciousness of number theory as a field of study. The development of much of modern mathematics necessary for basic modern number theory. Complex analysis, group theory, Galois theory, accompanied by greater rigor in analysis and abstraction in algebra. The rough subdivision of number theory into its modern subfields, in particular, analytic and algebraic number theory. Algebraic number theory may be said to start with the study of reciprocity and cyclotomy, but truly came into its own with the development of abstract algebra and early ideal theory and valuation theory. See below. A conventional starting point for analytic number theory is Dirichlet's theorem on arithmetic progressions, whose proof introduced L functions and involved some asymptotic analysis and a limiting process on a real variable. The first use of analytic ideas in number theory actually goes back to Euler, who used formal power series and non-rigorous limiting arguments. The use of complex analysis in number theory comes later. The work of Bernhard Riemann on the zeta function is the canonical starting point. Jacobi's four-square theorem, which predates it, belongs to an initially different strand that has by now taken a leading role in analytic number theory. The history of each subfield is briefly addressed in its own section below. See the main article of each subfield for fuller treatments. Many of the most interesting questions in each area remain open and are being actively worked on.